So let's next talk about hypothesis tests for a population mean, where we're dealing with what are called one-tailed tests. So far we've been talking about two-tailed tests. So we've had hypotheses that look like this. And what we do is we look to see if, let's say, the test statistic is too big or too small relative to what should happen if the null hypothesis was true. Now, with a one-tailed test, you're just going to look in, let's say, one direction, let's say too big only or too small only, corresponding to a set of hypotheses that are set up in a little bit of a different way. So, one-tailed tests. We're testing hypotheses like this. HO is mu is greater than mu0, or mu0 is some particular number. And HA, I'm sorry, let me restate that to make sure I got it right. HO is mu is greater than or equal to mu0. HA is mu is less than mu0. This is referred to as a left-tailed test. Notice how the inequality sign in HA is pointing to the left. That's a quick way to know that this is called a left-tailed test. And what this is basically saying is this, that you're going to have to be on the left side of this t distribution, if you think of it in terms of a test statistic, in order to reject HO. Why is that important? Well, take a look at y bar minus mu 0 over s divided by square root of n is our test statistic. We are going to need y bar to be less than this value of mu 0 in order to reject. So that means it's going to y bar minus mu 0 is going to have to be negative. That means you are going to need to be on the left side of that distribution. Now we could also have right-tailed tests. Right-tailed tests exactly the same as above, but we change these inequalities around. So we have less than or equal to as for HO. We have greater than for HA. Right tail inequality signs pointing to the right. Again, think of it this way. In order for mu to be said to be greater than mu0 based upon a sample, well, this y bar is going to need to be greater than mu0. And thus, y bar minus mu0 is going to be positive, and thus you're going to need to be on the right side of the distribution in order to reject HO. Again, the key element here is deciding, well, how far on the right side or how far on the left side do you need to be. That's where the critical value comes in. So let's talk about how to do these hypothesis tests. Doing the confidence interval method can be a little bit tricky at first, but in the end, it's not too bad. So we're going to state HO and HA. In step 2, find our confidence interval like before. But now, since we are only looking at one direction here in HA, we only need to do what's called a one-sided confidence interval. So for a left-tailed test, we find y bar plus the value from the t distribution. And notice how it's just alpha there, not alpha divided by 2, times s divided by square root of n. For a right-tailed test, you find y bar minus this value from our t distribution, this quantile, times s divided by square root of n. So, for example, let's say we have a left-tailed test. We will get just one confidence limit. It will be the upper limit, because notice how we have a plus there. And so if you have whatever quantity you're measuring, defined from, let's say, negative infinity to positive infinity, the actual confidence interval itself, like a 95% confidence interval, is called a one-sided interval, because on one end, you have, let's say, just infinity, the lower limit, or the upper limit, depending upon which you're doing. And the other end, you have the actual numerical value. Let me restate that. That might not have been clear. So if I have a left-tailed test, then maybe my interval is negative infinity to the number 2. And to do then the hypothesis test for a left-tailed test, suppose we have mu is greater than or equal to 3 versus mu is less than 3. Well, notice we are, let's say, maybe 95% confident that mu is basically less than 2. So in that particular case, then, we would reject HO because notice HA is mu is less than 3. So similar to what we did before for the traditional confidence interval, which would be called a two-sided confidence interval, we check to see if the hypothesized value was inside the interval. If it's not, you reject. If it is, you don't reject. Same thing happens here. We just have a little bit of a different looking kind of interval. Okay, so step 3, I just said that. And step 4, describe what 3 means in terms of the original problem. Now, sometimes students have a hard time understanding or having an intuitive feel, I think that's a better way to put it, for whether or not they should use the plus or the minus in a one-sided interval for a particular hypothesis test. And it all comes down to the following. Let's say that we were doing this left-tailed test, where notice in HO's mu is greater than or equal to 3, HA's mu is less than 3. Now, instead of using the correct interval, which would have negative infinity as a lower bound and the numerical value as the upper bound, suppose we reverse things. Suppose instead we would calculate an interval that looks like this. A numerical value for the lower bound and positive infinity for the upper bound. We emphasize this is the wrong interval to use here, but let's say that this was the interval that we use. So in other words, we use the minus version of that one-sided interval. B is some number. Now note here that if B was, let's say, negative 10,000, would we reject? Well, no, because mu greater than or equal to 3 is inside the interval. Suppose B was negative 2, would we reject? No. Suppose B was positive 2. Would we reject? No, because mu greater than or equal to 3 is inside this interval. Suppose mu was 4. Suppose mu was positive 10,000. Would we reject? No. So in fact, you would never ever reject HO if you use this kind of interval where you would take y bar minus the quantile from the t distribution times s divided by square root of n. So if you would never reject, then you must realize then, okay, this is the wrong interval to use. Instead, what I do need to do is look at the other kind of interval, which would be y bar plus then the rest of the stuff. So that's the intuitive way to understand, do I use the plus or the minus version of that confidence interval? Okay, so let's take a look at an example. So let's say a consumer group is concerned about a manufacturer's claim that their tires last on average at least 22,000 miles. Mustn't be that good of a tire if it only lasts 22,000 miles. A sample of 100 tires are taken and the number of miles that each lasted is recorded. The sample mean was 21,819. Notice it's less than 22,000. So you might be thinking, uh-oh, is this sample telling me that maybe this manufacturer's claim is incorrect? It depends upon the variability that we have for a y bar. Standard deviation of the data that was observed was 1,285 miles. And let's perform a hypothesis test to see if there is evidence. So we're trying to see, is there evidence to disprove the manufacturer's claim? So that statement there then controls how we set up the hypotheses. Is it going to be a right-tailed test or left-tailed test? It's very, very important because again, this, I should say again, but this is a particular location where students struggle with. Okay. Is there evidence to disprove the manufacturer's claim? So that's what we're trying to do and control the type 1 error rate at 1%. So since that's what we're trying to do, this is almost like a research hypothesis. Okay, we're looking with a sample, see if there's evidence to disprove the manufacturer's claim. So because of that, we need to put that aspect in HA. And the reason being corresponds to the type 1 error rate. We control the probability of making a type 1 error at alpha. So by specifying this part in HA there, we have essentially a 1% probability in terms of, like, let's say the repeated sampling process of take a sample, do a hypothesis test, take a sample, do a hypothesis test. We control the kind of making it, of coming up with the wrong conclusion here at 1%. Okay, so here's our hypotheses. Mu is greater than or equal to 22,000. Mu is less than 22,000 for HA. Then the corresponding one-sided interval would take y bar plus then the rest of those quantities. If you do all the math, you get 22,125. So despite the sample mean being less than 23,000 miles, the variability that one would typically have from one sample to the next is such that, hey, you could get over 22,000 miles for the population of all the tires. So confidence interval, negative infinity. You can't have a negative infinity miles, so you chop that off and make it 0 if you want to. Mu is less than 22,125. So because of that, since 22,000 is in that interval, do not reject HO. There's not sufficient evidence to disprove the manufacturer of tires claim. Okay. Well, what about then the test statistic method? State HO and HA, find the test statistic, just like how you would normally. So T equal y bar minus mu 0 over S divided by square root of n. Find the critical value. This is what changes. Now, since we are dealing with a one-tailed test, we only need to find one critical value. For a left-tailed test, you need to be on the left side of the distribution. We have a negative out in front of our quantile. And notice we only have an alpha there versus alpha divided by 2. Since we don't need to worry about being too extreme on the left side, too extreme on the right side of the distribution, now we only need to worry about one side of the distribution. For a right-tailed test, and we're pointing to the right, we have a positive value there. Then we need to decide if we reject or don't reject HO. So left-tailed tests, here's where our critical value is going to be. If anything's to the left, that tells us our sample has given us some evidence that we're just so extreme, so it would be so unusual to observe this evidence if HO is true. So therefore, let's conclude that HO is actually incorrect. We reject it. Right-tailed test, you could say a similar thing as well. Now you're going to be on the right side of the distribution, and then state your conclusions for step 5. So for the tire life example then, the test statistic ends up being negative 1.4. Our critical value, again, you can go to the QT function to find that. You would, in this particular case, let's see, you could put 0.99 there, a minus, and then your degrees of freedom of 99. That would be one way to find that. In step 4, let's graph things out. Here's where my test statistic falls relative to our critical value. This isn't really extreme. This would not be unusual to have this particular sample if HO was true. So therefore, because negative 1.4 is greater than negative 2.364, don't reject HO. Thus, there is not sufficient evidence to disprove the tire manufacturer's claim. Okay, next, let's talk about the p-value method. Step 1, HOHA. Step 2, find that p-value. Of course, you're going to need to calculate the test statistic first, then define the p-value. Left-tailed test. Notice how when I find that corresponding p-value, that probability value, I need to find the probability that a random variable t is to the left of what I actually observe. Right-tailed test, the inequality sign out is pointing to the right. And just as a reminder, what does a p-value give you here? Well, for a right-tailed test, it gives the probability of finding a value of t at least this great, assuming HO is true. Step 3, state your alpha level. Step 4, decide if you reject or don't reject. The same way as we've done before. P-value less than alpha, reject. P-value greater than alpha, don't reject. And so this is how things could look for a particular right-tailed test. Notice how my t-test statistic here is in more of the middle of the distribution here. So I calculate this area underneath the curve. I compare it to my alpha, and we can see the p-value would be greater than alpha. And step 5, state your conclusion. Okay, so we're on page 9 here. Entire life example, once again. Test statistic was negative 1.4. I have a left-tailed test, so I need to find a probability then that the random variable is less than negative 1.4. That probability is 0.0823. How do I find that? I use the PT function. But again, one could actually use calculus to do that as well. Excuse me. Alpha is 0.01. Then, because 0.0823 is greater than 0.01, don't reject HO. So therefore, there is not sufficient evidence to disprove the manufacturer's entire life claim. Okay. Now let's talk about some important things here. In terms of interpreting a p-value, and this goes the same in terms of the confidence interval. If you remember with the confidence interval, well, mu greater than or equal to 22,000 was inside the interval. It was kind of towards the borderline as well. And also, when we did the test statistic, if you remember, I used alpha 0.01. So if we use the critical value, I get a critical value about negative 2.3. But let's say instead I use a different critical value. I'm sorry, a different alpha level. Then that critical value is going to be much closer to what our test statistic of negative 1.4 was. Okay. Now, to interpret this p-value, if mu is really greater than or equal to 22,000 in the population, then a test statistic value t, no smaller than what was observed, would occur about 8% of the time. If the hypothesis test process is repeated a large number of times, that's what that means. Now, it may occur about 8 times out of 100 to have something like this happen. This is somewhat, you could say, borderline with regard to what is a likely event. Is 8% a likely event or not? Here, we used the judgment of alpha 0.01 to make a determination of if alpha is 0.01, if alpha is greater, if the p-value is greater than 0.01, then we judge it's a reasonable event to happen. If p-value is less than 0.01, then we say, well, that's unlikely to occur. But you can see if you change the alpha, you change your interpretation. And so this is something that I want to discuss. When I have a p-value that's close to whatever I state alpha to be, even if the p-value is greater than alpha, I will say, well, there's essentially marginal evidence that the null hypothesis is true. It's definitely not strong, but there's marginal evidence. Maybe it'd be worthwhile to do an additional study to make the judgment of can the research hypothesis be proven true. On the other hand, if I had a p-value that was less than alpha, but was still close to what the alpha value was, I would say basically the same thing. There's marginal evidence that the null hypothesis is incorrect, and so therefore probably further study needs to be done. To give you an example of this and how to interpret p-values properly, and how some people have had problems with interpreting p-values, how they can be misinterpreted. I'm going to talk about an example dealing with HIV vaccines. So a few years ago, there was a study done that was a clinical trial that was investigating, did a newly developed vaccine for HIV, did it actually work? Did it help prevent HIV infection? So what was done in this clinical trial, I think it was about 20,000 people were given this vaccine, I think it was in Thailand, and they were observed over a few years to determine, did they actually come down with HIV or not. There was both a group of people that actually received the vaccine and a group of people who did not receive the vaccine, received what was called a placebo. And what these researchers did was they compared the group that did receive the vaccine to the one that did not. Did the one that received the vaccine get infected with HIV less than those who did? And in order to make inferences to the general population of all people around the world for whether or not this HIV vaccine worked based upon the sample, inference methods were used. In particular, a hypothesis test was used. And for the main thing that they were looking at, they had a p-value of about 0.04. And of course, if you compare that to an alpha of 0.05, you would reject HO, where HO is, it does not work. HA is the vaccine works, without going into all the symbolic details. So the p-value was less than alpha. So they said, hey, this vaccine works. And this made international news. It was like on the front page of most newspaper websites. It was covered on TV. And obviously, it was a very important finding that this was the first time, in fact, that a clinical trial has shown that the vaccine did indeed work. And again, the main conclusion was based upon this hypothesis test. Now, this information was released, I think, either by the journal or the university that was conducting the clinical trial. It was released before the paper that was actually written by the researchers was actually put into print or put into the journal. Now, a month later, the paper is actually published, corresponding to this clinical trial results. And they looked at another analysis, in addition to the analysis that gave a p-value about 0.04. They looked at another analysis that also gave a p-value of 0.06. Basically, the difference was maybe about, I think it was about 7 individuals were removed from the data set that ended up with a p-value of 0.04. When they were put back in, the p-value was now 0.06. Obviously, if we use alpha 0.05, we would say do not reject HO. And again, once this was released, this made news again, although not front page news anymore. It was like buried down on the website to say, hey, well, maybe we shouldn't have been so excited about those results, because now there's not sufficient evidence to indicate that indeed the vaccine did work. But if you look at these p-values, they're very, very similar. You know, it just so happens one's on the left side of 0.05, one's on the right side. But they're very similar. And so the correct conclusion, actually, to make in this particular situation would be to say that there's actually marginal evidence that the vaccine worked. It's definitely not strong. It's definitely not conclusive. But we're getting a p-value that's low. Because I have a p-value low, that says what I'm observing is somewhat unusual. But it's not necessarily really a strong, unlikely event to occur. That would have been the better way to approach this, rather than rely on a strict alpha 0.05 to make that judgment. If you have any questions about that, I'd be happy to discuss this study more and to re-emphasize my point here. I want to emphasize, though, that I bring this up is because over the last few years, there's been a lot of critical statements made about hypothesis testing, and a lot of those statements are because of people misinterpreting what the hypothesis test is giving. And if one better understands that, just because your p-value is 0.04999999 doesn't mean that you have necessarily proved your research hypothesis to be true. On the other hand, just because your p-value is 0.05000001 doesn't mean that you have to throw away all your research that you've done. Okay, let's move on. Let's go back to the volleyball example once again. Without a particular reason why, let's say my HA is going to be mu is less than 11.6, so I have a left-tailed test. If I were to use a t.test function with it, note that there's an argument in the t.test function that allows you to specify if you have a left tail, right tail, or two-sided test. We've actually seen the two-sided test before. But now I have a left-tailed test. Rather than saying left, instead we use the argument alternative equal less to mean that. If you have a right-tailed test, you use greater. So with this then, everything remains the same except for, here's my p-value, 0.2726. So this is representing the probability random variable t is less than negative 0.6. Notice here's my interval. It's now a one-sided interval. So I go ahead and do the test. Again, here's my interval. Notice that 11.6 is actually inside that interval. So therefore, I do not reject HO. There isn't sufficient evidence to indicate the mean radius is less than 11.6. My Excel file that I created and showed you in the last set of notes is set up to allow you to do these one-tailed tests as well. Please go into that file and experiment with it to see how the results change depending upon what Y bar is or what S is and so on. By doing that, you'll get a much intuitive feel for how these hypothesis tests are actually working. Okay, so this takes us to page 13 then. We're going to deal with car warranties. So every new car that you get has some kind of warranty attached to it. Very frequently you hear something like a 3-year, 36,000-mile warranty, which basically means whichever comes first, either 3 years or 36,000 miles, that's when your warranty ends. And one dealership believes drivers tend to reach the 36,000 miles before 3 years of ownership for a particular type of car. And they are basically using this then essentially as their research hypothesis. And so what they do is they go and ask some people who have purchased their car and they've had it now for over 3 years. And they ask them, well, at 3 years exactly, how many miles had you driven? And based upon that, they asked 32 owners. The sample mean was 39,900. The standard deviation was 1,866. So notice how this 39,900 is definitely greater than that 36,000. So right from there, you might be thinking, oh, based upon this sample, something must be up, or something may be up, I should say, in terms of maybe this sample is telling me that indeed these owners of these cars reached 36,000 miles before, meaning that their warranty ends before that 3-year period. Okay. So here are the hypotheses in. Since we're interested in showing that the mean is actually greater than 36,000, that's why the alternative is written like this. Let's think about what the type 1 and type 2 errors would be. Type 1 error. You reject mu is less than or equal to 36,000, but mu is really less than or equal to 36,000. So the sample is telling you that, hey, mu is greater than 36,000, but you were wrong because in actuality, it was less than or equal to. So that is the kind of error that we're trying to control here, the probability of making that particular error. We're controlling at an alpha level of let's see, I think we end up using 0.05 for this problem. I'm sorry, 0.01 for this problem. Excuse me. Okay. So the probability of this happening, of getting this error is alpha. The probability of correctly rejecting HO is 1 minus beta. Remember what this represents. It's also called the power. More on power later in the course. Type 2 error. Do not reject HO, but HA is really true. So mu is, based upon our sample, we say, okay, I can't say that mu is less than or equal to, I cannot reject mu is less than or equal to 36,000, but in fact, it was. And so that is an error, but we don't control the probability of making that kind of an error. Okay, so step 2. Part 2 here. Let's perform the hypothesis test as at a level of significance of 0.01. In other words, alpha 0.01. And so we state our hypotheses. We find our test statistic based upon the available information to us from our sample. Test statistic is 11.82. This is quite large. Corresponding critical value from our t distribution. I go to the QT function once again. I get 2.453. So, test statistic is greater than that critical value. Therefore, I definitely reject HO. There's strong evidence there. So, I state in the following, in terms of the original problem, there is sufficient evidence to show that the average miles driven in 3 years is greater than 36,000 miles. If I were to do the p-value method then, now the p-value is the probability of a random variable t being greater than 11.8, and as you might expect, that probability is extremely small. So to interpret that p-value, just for emphasis, if mu was really less than or equal to 36,000 miles in the population, HO is true, then a test statistic value at least this large would occur 0.0000, so many 0.02544% of the time. If the hypothesis testing process, meaning taking a new sample, performing a new hypothesis test, is repeated a large number of times. Since this is very unlikely to occur, to actually observe a test statistic like this. Therefore, most likely mu really is not less than 36,000. Mu is greater than 36,000. So step 3, we state our alpha level. Step 4, p-value less than alpha, therefore reject HO. And then step 5, well, there is sufficient evidence to show that the average miles driven in 3 years is greater than 36,000 miles. Confidence interval method, please make sure you do that on your own to verify that indeed you can do it. So from a customer's viewpoint, should they expect to have their car to be under warranty for 3 years? Well, no, because they're likely to, it looks like on average, they're going to hit that 36,000 mile mark before they hit that 3-year mark, because at 3 years, their average number of miles driven is greater than 36,000 miles. Okay, some final notes here. Students usually say that deciding what goes into HO and HA is the toughest part of hypothesis testing when dealing with one-tailed tests. Remember, the equality part always goes in HO. And also, always ask yourself what the type 1 error, write it out, what that would represent, and let that help guide you for what you want to control the probability of in terms of an error. That will then guide you to determine what goes into HO, what goes in HA. That is the key. These kinds of hypothesis tests that we're doing here are often called t-tests because we're using the t-distribution with them. And lastly, here's a little sheet that helps summarize then the hypothesis testing steps. Please use this as needed. So then that concludes then doing hypothesis tests with a one-tailed or one-sided version of the test.